In this video, I'm going to introduce the density curve, right? So, a density curve, what this is it's a graph of a continuous probability distribution function. So, continuous probability distribution function. So up until this point, we have talked about probability distribution functions. Though when we've talked about them, we've talked about, instead of continuous, we've talked about discrete probability distribution functions, right? So we've talked about like a general sort of discrete probability distribution function represented using a table, right? So for particular values of x, you calculate the probability probability of x, you list out the probability distribution this way. Also, we've talked about the binomial probability distribution, right, which is a formula, and we've talked about how to calculate the probability that x will equal certain discrete numbers like 1, 2, 3, right, based off of this formula. But what if x is not discrete? So in these two cases, x is discrete. Well, when x is not discrete, we will represent the probability distribution function instead of using a table or a formula. I mean, there are formulas, of course, but instead of using the formula, a lot of times we just go and we look at the curve. Okay, so in this class, we're actually going to be focusing mostly at looking at the density curve. And the density curve is a way to represent the probability distribution function, just like how this table is a way to represent the probability distribution function for discrete random variables. All right. So, few properties that density curves must comply by. The total area under the curve must be equal to 1, and every point on the curve must have a vertical height that's more than or equal to 0. One density curve that you're probably already familiar with is the normal density curve. You probably have seen this drawn out before, right? This bell-shaped curve. So this is the normal density curve, right? So what is a density curve really? Well, it's kind of like a relative frequency histogram. So a relative frequency histogram is for a sample, right? A density curve is for a population. Right? So, for example, I have here a relative frequency histogram for the height of trees. Okay, so it looks like 10% of the trees are between 0 and 5 feet tall, 20% are between 5 and 10, 40% are between 40 and 15, 20% are between 15 and 20, 20 is between 10% is between 20 and 30, right? And one of the things you'd have to check when you were doing this relative frequency histogram, you want to make sure that all the percentages add up to 100%, right? Because this basically represents the entire sample. All of the trees were between 0 and 30. 30. I guess I should put a unit here. This is feet. Okay, so between 0 and 30 feet. 100% were between 0 and 30 feet. So the total, if you were to add up all these percentages, 10 plus 20 is 30, plus another plus 40 is 70, and then another 20 is 90, plus 10 is 100. So all of the percentages should add to 100%. 100% of the sample is represented here. Okay, so similarly, when you're thinking about a population, when you're thinking about the population, you're thinking about the density curve, here is the value of x, right? So you'll still have 0 to 30, and then what you'll have is like more like a continuous like line like this, right? And so there'd have to 100% of the data. I mean, 100% of the population is between 0 and 30. So all of so it must the area under this curve must add up to 1, right? So the area, just like how these total percentages must equal 1, the area under this curve must be 1, right? And so this is instead of this being relative frequency on this axis, now this is the probability distribution function value. So usually it's represented with like an f of x or something like that, right? Sort of like how this is p of x, right? P of x. Now it's like some function value f of x, right? And so another thing, that explains why the area under the curve must equal 1. It's very similar to how these total percentages must add up to 1. Same thing goes here. This total area must add up to 1. Okay, another thing is that the curve must have a vertical height that is more than 0, right? And so notice I kind of like stopped this curve right here at 0. And so for this theoretical population I came up with, it's impossible for any trees to be less than 0, have a height less than 0, which that's true. And then also it looks like for this tree, since I stopped the density curve, it's impossible for any trees to be more than 30 feet. Okay, so what's going on here? Why does the curve must have a vertical height that's more than 0? Well, because if it went below 0, it's kind of like having a bar that went below 0 in the relative frequency histogram. So maybe a negative 10%, right? That doesn't make any sense. The proportion of trees that are between 0 and 5 feet, if it were, the proportion cannot be negative, right? The proportion of trees that are between 0 and 5, it must be a number that's going to be between 0 and 1. So so the vertical height must not go below 0, and actually it also won't go above 1, and so it won't be higher than 1 because probability is constrained between 0 and 1, right?